do the tests, the only tests in this textbook about categorical data. So today we're going to be looking at the chi-squared goodness of fit test, abbreviated GOF. And then next class we'll look at two other chi-squared tests, which is the chi-squared test for homogeneity and the chi-squared test for association independence. So those tests we'll do next class, and I'll discuss them next class. That's in 11.2, and they're done the same way, so that's why we're going to do those in the same note packet. But first, to start with this chi-squared goodness of fit, which is also very important on the AP Bio test. It's included on the exam, and I know that there have been years where it's been on the exam. This test lets us look at, is categorical data fitting what we expect those categories to be? So let's look at this. Mars makes candies. It makes the M&M milk chocolates, and they say that their bags of candies are going to contain 13% of browns and reds, 14% of yellows, 16% of green, 20% oranges, and 24% blues. So that's the claim that they say is true about this. So we go and we get a bag of candies, and we come and we count how many of each of these colors there are. And for example, we get 9 blue candies, which the statistic that we're getting for that. So notice that there's a hat on there. I get 0.15. How does this compare to the 24% that they claimed? Now, we could then do a test, one sample Z test for a proportion to compare blue to the null hypothesis of 24% blue. That would only tell us about the blue. Then we'd have to run the test again to look at the orange, and again to look at the green, and again to look at the yellow, and you get the idea. We would basically have to do 6 tests. But what if their results, some of them said there was evidence and some said there wasn't evidence? How would we conclude about the whole situation? Results. So because that wouldn't really tell us, it would only tell us about one color and how that one color fits. It wouldn't tell us how the bags are fitting to the general overall categorical claim that they have stated. And so in order to do a test of this categorical and doing all the categories at the same time, what we do is a chi-squared goodness of fit. Use chi-squared goodness of fit. All right, so on to the next page. So in order to do this test, because like the Z test isn't going to tell us how these colors differ as an overall distribution, what we do is we do this chi-squared, where the null hypothesis is that our null is that the company's stated color distribution is correct. And the alternative hypothesis is that we have found enough evidence to reject the null hypothesis, and we have evidence that their distribution is not correct. So we could write that in words, or we can write it symbolically, and you can see that I have all the different proportions listed because we're testing all at the same time. And all we need is one of the colors to not match, and then that would make us have enough evidence to reject the null and to say that that we're rejecting the null and that we have evidence of the alternative. So first thing we're going to have to do is we're going to have to test what we've observed. Okay, so we're going to have counts. We can't use proportions. We need observed. And we're going to compare that to expected. And if we have any decimals for the expected, keep them. Keep the decimal, okay, on those expected counts. Let's go to the next page. Just kind of running through these note pages. Okay, before we do anything, we always check our conditions. And so in a chi-squared test, it is not nearly normal. So definitely never say that it's nearly normal. Let me cross that off because you'll never say that. But instead, what we need to have is enough data that we feel like we have a good idea of what the distribution's doing. So we call that the large enough condition. So instead of nearly normal, TION, you're going to say the large enough condition, and that's basically speaking to the sample size in each of the categories. And that needs to be 5 or more in order to be able to be large enough to do that. So we're going to need to be greater than or equal to 5 in order to have that. So as long as each of those expected counts are at least 5, you're going to be able to run a chi-squared test with degrees of freedom of the number of categories minus 1, not the n. So df does not equal n minus 1. Okay, so it's not that. It is df is equal to categories minus 1. How do we find that chi-squared test statistic? What we want to do is we want to look at how do the observed values that we gathered in our data vary from what is expected theoretically based on the null hypothesis. So, and it looks a lot like your standard deviation, where you basically, you take your observed and you subtract your expected. You're going to square it because you want it to be positive. And then you're going to divide that by your expected, and that's going to get you your chi-squared statistic for each individual category. Each individual category's chi-squared, how far off observed appear to be from expected, then gets added together, and that makes the sum of your chi-squared. Then you come down here to the graph, and let's say your sum of the chi-squared, when you added them all up, let's say it was equal to 9. Well, then you would go to your graph here at 9, and you would wonder if, based on your degrees of freedom, what is the area of the tail? Because this is right skewed, we're always testing that tail on the right. So this is our test area. And we're going to compare to whatever alpha level we want. So is that area in the tail at degrees of freedom? Maybe it's a little smaller, but with the low degrees of freedom, it'd be hard to get a chi-squared that's some of the chi-squareds that's very large. But is that area more or is it less, greater than or less than your alpha? And that's going to be your idea of whether or not you're going to reject. And if you see here, how do we punch it into the calculator? Just like with normal CDF, just like TCDF, it looks a lot like that. we have the chi-squared CDF, and you basically, if I was doing this for the 9 and I wanted to know my area, I'd go 9. You're always testing the right tail, so let's put in 1,000 just because that's some random large number. And then let's say my DF was, well, whatever my DF was, and then I would get, an area, and that would be what I'm going to compare to alpha. So now we'll do an example with the M&M's chocolates just to see if that's meeting. We're going to perform a chi-squared goodness of fit test at alpha equals 0.05 for the candy. Remember that just like in any test, we always start off with conditions. And so let's start off with that. So let's move this up here. Okay, so for conditions, we need, first of all, that things are random. And I would say it said that it was a random bag. Okay, so that was random sampled bag. That was given. That's good. Okay, so now we got to do independence. So this is feeling kind of familiar. Dependence, I guess, independent. 60 candies is less than or equal to 10% N if more than 600 candies, which seems reasonable. So that's met. And then it is not going to be the nearly normal condition. Instead, what we need is the large enough condition. So large enough. So to do this, we're going to mean, whoops, I spelled large wrong. Large enough condition, we're going to have to check expected counts. So, okay, so let's go up and see if these are all going to be bigger than 5. So they didn't give us expected counts, but they did tell us that 24% are blue, 20% are orange. This is what the null is. Green, 0.16, yellow, 0.14, red, 0.13, and brown, 0.13. So to figure out the expected, we would take the proportion and we'd multiply by the n, and that would be our expected. So, and if there's any decimals, we're going to keep that. So my n is 60 in this situation, so that means I get 14.4, and I'm going to keep that. I'm going to keep that number. And I go down, and each one of these needs to be multiplied by 60. Now there's a fast way to do that in the calculator, because if I have the data in my calculator, I can very quickly multiply these things out. So, which I'm going to do in a second. I'll show you how to do that. I'll show you how to do the whole thing on the calculator. But for now, these are the numbers. So I will show you how to do that. And I, just so you know, I have this in my L1 and I have these proportions in my L2. But I will show you how to do that. So now when you look through these, notice how you want to keep the decimal. That's very important. They will mark you wrong if you get rid of the decimal. All my categories are above 5. So these are greater than 5. Now, if one of them wasn't, then you could combine your categories. Like, for example, let's say red and brown. Let's say that they weren't big enough. What I would do is I would combine the categories and I would call it red-brown, and I would combine them so their observed would be 16, and their expected, I mean, theirs was fine, but their expected would have been 15.6. So like you can do that. If you find that your expected counts are not high enough, then you have to combine categories together to make them high enough, and then you can run that. And what would happen is my DF originally, when I look at this, I've got 6 categories. My DF is going to be 6 minus 1, which is 5. But if I were to do this new situation, my DF, whoops, that's a very messy looking DNF, would be equal to 4 because I would have reduced my categories down 1 category. But I'm going to erase this because luckily all my counts were greater than 5. So I'm going to come down here, and so check expected counts, all counts greater than or equal to 5. So now what do I have? I'm going to say that the conditions for inference met. What am I going to do? For a chi-squared GOF test. Okay, so that's what we're going to do. We know what our degrees of freedom are, and so now we're going to go and find all these chi-squared values. And so now I'm going to switch to the calculator so I can show you how I would do this with the calculator, how I'd find these chi-squareds really quickly. And then we're going to put these chi-squareds right here. We're going to write them all right here, so in the column next to this. Okay, so to the calculator. Here's a formula sheet where you can see the chi-squared test statistic, the formula for that right here for each item. Here I have entered into the calculator my observed counts, and I always like to put those in first, just like I do for when I do linear regression. And then here are my expected percentages. But what are my expected counts? I'll go L2 times 60, and you can see that's how I got those numbers really quickly for that. And then now, being mindful of what the formula is, that I'm going to take my observed and subtract my expected and then square them. So I'm going to start my parentheses, and I'm going to take the L1 list and subtract the L3 list. You are not able to work with the proportions. You must work with counts in order to do this test. I am going to square it. Then I need to divide by make sure you divide by the correct thing, the expected. So let's divide by the L3 list. And those are the chi-squared contributions for this goodness of fit test. Now, all of these together are what we are going to be looking at for evidence. And when I look through the values, I can see that this category with the chi-squared of 5.18 or 19, that one that's contributing a lot of the evidence if there's enough evidence. Now, if I want to add up the L4 really quickly, remember that a quick way to add those things up would be to go back to your main menu and do Calc 1 var stats on the L4 list. Going down, make sure your frequency list is blank. And then I can see that the sum of those was a 10.179. So look, let's call that 10.18. So now I'm going to write all those numbers down on my paper. Okay, and I've already written down the L3 list, but now I'm going to write down all the chi-squared contributions. So 2.025, 1.3333, 0.6, 5.1857. There's our largest contributor in the yellow category, blue being the second largest contributor, 0.62051. And it's good to be aware of those things. 41538, and the sum of our chi-squareds. And chi, the way you draw that, it's a Greek letter, make a sort of curvy looking X, 10.1799. Is that enough evidence then to reject the null? Oh, whoops, we never wrote our null and alternate hypotheses. That's not so good. Well, let's write those right now. Okay, so my null hypothesis is that the stated color distributions for Mars candies is correct. My alternative hypothesis would be at least one color does not fit the overall statement. Okay, and I've just found my chi-squared. So now I am going to test the probability that a chi-squared is greater than a 10.1799. Let's find out what the probability of that is. To hopefully quickly go to my calculator. I'm going to do the chi-squared CDF. So, okay, so in the calculator, just second and vars gets you to the distributions. Scroll down to number 8 on my calculator, which says chi-squared CDF. Down to there. The lower amount is always going to be, a right-tailed test, so 10.1799. Upper, any large number will do. Degrees of freedom, there were 6 categories, so 6 minus 1 is 5, and then we paste it, and so there you go. Larger than 0.05, so that means we do not have significant evidence, even though those yellow M&Ms really seem to contribute a lot. With the degrees of freedom of 5, it was not enough to reject the null hypothesis. So, and if you do reject the null hypothesis, you do need to discuss which categories were the largest contributors. So in this situation, we are not rejecting. So, okay, so let's write our conclusion. Since the p-value of 0.0703 was was greater than alpha equal 0.05, we fail to reject the null hypothesis, and there is not significant evidence. Make sure you use the alternative hypothesis wording that at least one M&M candy color is not agreeing with M&M's or Mars candy's statements. Candy statement. I don't know. There's probably supposed to be an apostrophe, something in there. Okay. Now, if we had found the evidence, we would have wanted to discuss which one was contributing to that. Now I'm going to show you how to do this on the calculator, which will take you 2 seconds. And then in the next video, I'll do 2 examples, and there's at least one of them where we do reject. And in that example, I will show you how to talk about the largest contributor. So before I go to that, to the calculator, where I'm going to run this as a goodness of fit test, because all of your examples, they will match perfectly, except for that 10.2 t-test because of the degrees of freedom. But anyway, so under stat, tests, and if you scroll down through your tests, down a ways, you'll see there are 2 chi-squared tests. The first one chi-squared test is going to be your homogeneity and your independence, which we're doing in 11.2, chi-squared goodness of fit, which would be great to know for the AP Bio test and my test. Okay, so I've got my observed counts. Now, my expected were not in L2, they're actually in L3, so I do need to fix that. I have degrees of freedom of 5, maybe because I've used this before for this, I'm not sure, but I'm going to hit calculate, boom, and you can see that you get your chi-squared. There's the sum of the chi-squareds, which I already knew. Here's the p-value, which I knew. I've got my degrees of freedom, which I had to input. But then you can also see that you can scroll through and you can actually see all the contributors. These are the chi-squared contributions. Recognize those numbers that I have already listed. I find that it's easier to just do the chi-squareds in my calculator in the list and then to copy them down into a list. But they do show up right here if you need to see what the contributors were. And how does this compare to a simulation? So remember, simulation is when you do some kind of a model where the null hypothesis is the way the model was set up, and then you go out and you take samples and see how many samples are doing what you have observed or more extreme. So like, for example, if I had Fathom, which is a computer modeling system that then could make a model where it really is 24% blue and it really has those percentages of candies in this tremendously large candy machine. And if I were to do that and do 500 trials with this machine where it really is doing that, I would have found 37 of them that gave me a sum of the chi-squareds of a 10.180 or more. So 37 of these were to do that. So how does this compare to our p-value for our results? So if I say my p-value from the simulation, where the sum of the chi-squareds was greater than a 10.180, there were 37 times that this happened out of 500 trials, and that would have given me a p-value or probability of 0.074. So the empirical probability from this experiment, it's really only this 0.074, which is our empirical, is only how much higher? It's only 0.0037 higher than the theoretical of that we just got with the chi-squared test of 0.0703. So that's from that goodness of fit test. So simulations are another great way to compare and test the situation to see if you have evidence that something should be rejected. But in this case, we don't have enough evidence to say that it's unusual. So again, we would not reject what Mars Candy said about their color proportions.